This program is a presentation of UCTV for educational and non-commercial use only.
So we have three speakers tonight. The first is Joel Kramer. Joel I've worked with since I've come to UCSF in 1998. Joel is a professor of neurology and runs our neuropsychology division. He is a world's leader on healthy aging, and he's aging very healthily himself. He's, I think, a role model for all of us. We're going to see how well his brain is aging because he has to use a Mac computer, which he isn't used to. But if he can't learn that, then I'm really worried about him. So Joel is going to talk about healthy aging of the brain. I should also say that the NIH has asked Joel to develop new tests for testing the frontal lobes as we age, and his tests go from ages 3 to 90. And increasingly, they're going to be part of clinical trials for everything from attention deficit disorder to Alzheimer's disease. Next speaker is Virginia Sturm. Virginia's about to join our faculty at UCSF as assistant professor. She was one of the first employees at UCSF. She was a research assistant, interested in psychology, went on to get her PhD at Berkeley with Bob Levinson, studying emotion. She's an incredibly deep thinker, and she's going to talk about a lot of good things that happen to us when we age. I think it's a topic that we've really ignored. And then the final speaker is Howard Rosen, who's associate professor of neurology here at UCSF. Howard's also become a major leader in thinking about imaging of the brain, leads large international initiatives thinking about longitudinal changes in the brain, and he's going to talk about transitions from healthy aging to what we call mild cognitive impairment. So, Joel, thank you.
So thank you all for braving the elements to get here. Bruce should actually start to worry soon, since I'm not quite sure which buttons to push, but we'll figure it out. So I want to talk a little bit about what happens when we age, what happens to brain structure, what happens to brain function, and when I'm talking about brain functioning, I'm mostly referring to cognitive abilities. So it's actually fairly controversial. There's no consensus on what exactly are the key changes that we see with our brain structure and brain functioning. There are some very clear competing views, and I thought that we would refer to the experts here to describe what some of these competing views are. So first we have Betty Davis, who said, aging is not for sissies. Okay. Aging is a process of continuous decline in physical and cognitive functioning. In contrast, we have, on the other spectrum, at the other end of the spectrum, Betty White, who said, hey, the older you get, the better you get. So which one of these folks is going to rule the day? So what's the Betty Davis view? So let's look at some of the evidence that speaks to what are these age-related changes in the brain and how they might impact some of the day-to-day cognitive functioning that we rely on so much. So first of all, are there age-related changes in the brain? And the answer is certainly yes. Now, so last week they talked about several different brain regions. One of the more important ones from the memory and aging perspective is the hippocampus. This purple region here, and wouldn't it be great if everything was so nicely color-coded in a real brain? But the hippocampus is a critical region, and the areas surrounding that are critical regions for our ability to learn and remember new information, which I hear quite often in our aging population is something that does seem to change over time. Well, are there changes in the structure with aging? So here are some data from our aging control subjects. And as you can see, we've got hippocampal volumes plotted up here. You've got age down here. And you can see that there is a fairly linear trend downward, suggesting that there are certainly some changes in hippocampal volume as we get older. Well, I mentioned that the hippocampus is really important for our ability to learn and remember new information. So the next question, of course, is, well, are there age-related changes in memory functioning? So I think Kate Posehn last week talked a little bit about a favorite memory paradigm of ours in which we give someone a list of words, we give them several opportunities to learn the list of words, and then 10, 20, 30 minutes later we say, hey, tell me all the words on that list. So here are some of the data. Again, it's a 16-word list, and this is a study of about 1,000 people across the age spectrum, and this is how many words they were able to recall after a 20-minute delay. So again, the same age-related changes that we saw in our hippocampal volumes, these are being paralleled by the age-related changes that we are seeing in human memory performance. Education is controlled for in these graphs, and gender is controlled for, IQ is controlled for, and you still see these similar age-related declines. So some other brain structures that were talked about last week. I'm sure Kate Posehn talked a lot about the parietal lobes because she talked about spatial cognition. And Bruce earlier was talking about the frontal lobes. And you can see we're talking about a fairly large swath of cortical territory here. So how well did these regions fare with typical aging? Well, again, we see some sad support for Betty Davis's point of view. So even with the frontal and parietal lobes, you can see some age-related shrinkage in those regions. And then the next question is, well, do we see some parallel changes in cognitive functioning? Well, what do the parietal and frontal lobes do? Well, they do quite a bit. They're involved in a broad range of cognitive abilities, but one of the skills that we associate with the frontal and parietal regions are things like executive functioning, and by that I mean the ability to multitask, the ability to reason abstractly, to problem solve, to generate novel solutions, to inhibit inappropriate or irrelevant responses. These are all part of executive or cognitive control. So one of the things we want to be able to see is, are there age-related changes here? Well, we have a lot of different ways of assessing that. And a very simple way is to give people stimuli like these, where the task is simply to name the color of ink in which those letters are printed. And I doubt if anyone here in the room, except if you're colorblind, is going to have any difficulty noting that this is blue. And then later on, we give them a very similar, or sort of blue. It's supposed to be blue. It's this MAC thing. And then a very similar condition where, again, you're supposed to name what color ink the letters are printed in, but now you have to inhibit that tendency, that very overlearned tendency on our part to read the words. So this is requiring attentional or cognitive control. It's an ability that very much relies on that frontal parietal network that you heard about last week and are going to hear a lot more about next week. So the question is, do we see any age-related changes in this capacity to inhibit our attention to what's essentially irrelevant? So we can graph this interference effect. To what degree is someone's performance affected when they have to inhibit that reading response? And again, in this case, the higher it is, the slower someone is as a result of having to control their attention. So perhaps there are some age-related changes in our ability to modulate our attentional control. Well, this is 2011, right? It's really all about networking. It's all about connections. So how are the connections in the brain holding up? So a very important part of this neuron is something called the axon. This is an extension of the neuron that enables it to communicate with other neurons or other parts of the nervous system. And to improve the ability of this axon to communicate information, most of our sort of longer and thicker axons have this fatty sheathing with its myelin sheath that improves the way in which it functions. Well, if you actually look at either a fresh brain or a brain on an MRI scan, what you'll notice is that these parts of the brain look white. So we'll be referring to these as white matter. And as you can see, there's a fairly large amount of our brain that is white matter. And these are full of these fibers, these bundles, these tracks of axons that are basically, this is Comcast cabling, or the telephone lines that enable different parts of the brain to communicate with one another efficiently and effectively. Well, how are these connections holding up with aging? Again, we can go back to our sample of elderly controls that and elderly, by the way, is my age plus 1 year. How they do it, and we do these fancy images on all of these. And again, what you can see is there's some thinning, some changes in the white matter on our imaging, and we now have some fancy imaging that can look at the microscopic integrity of the white matter, and again, you can see a very similar age-related change in how that's working. So our white matter is important for a lot of things, but certainly one of the things that's important for is our ability to move information around quickly. So if we're going to try and understand what potential effects changes in white matter might have on cognition, we would certainly want to look at information processing speed. Does our speed of information processing change as we get older? And again, the higher the score on the processing speed, the slower one is being. And again, in a group of typical aging subjects, you start to see some dramatic changes, or not dramatic, but significant changes in the speed with which information is being processed. All right, so that's the Betty Davis view. And if you hearken to that view, the cortex is getting thinner, our white matter is getting thinner, in some cases our hair is getting thinner, so it's not a pretty picture. So let's hear what Betty White has to say to balance the overall picture. All right, so here's the Betty White view. Remember, the older you get, the better you get. So we took around 140 older control subjects that we followed through a multi-center study of aging and brain functioning. These were folks who were on average 73 years old at baseline. Now, we had a couple of different scores on these folks. I'm going to show you some data from the memory score. So there are several different memory tests and conditions. We summed them all up. We generated a memory performance. And again, these folks were followed on average about 8 years. So every few years, we brought them back in for a follow-up assessment. And what we see here is that there's absolutely no evidence for an age-related decline in these folks who were followed longitudinally. Not only were they all pretty much in the average range at baseline, but again, 4 years later and 4 years after that, if anything, although it's not statistically significant, it looks like they're getting a little bit better. Very encouraging, and a very different story than what you get when you look at a big cross-sectional study that conforms more to the Betty Davis point of view. And there are also lots of skills that don't seem to change with age, even in a cross-sectional study. So again, this is a study of about 1,000 people looking at a measure of vocabulary. And as you can see, that not only does vocabulary seem to increase into our 50s, but it's pretty stable after that. So there are plenty of reasons to support the Betty White point of view. So how do we resolve this battle of the Bettys? Well, I think that my answer to all of this is that they're really asking the wrong question. The question is not, does our brain change with age, or does our cognitive function change with age? The question is, when it does change, why is it changing, and what can we do about it to make sure that it changes as little as possible for as long as possible? So here's a slew of longitudinal data, similar to the aging data I showed you earlier. And what you can see is that when you take any population of folks, follow them longitudinally, there will be a very large subset, in many cases the majority, of folks who don't really show any age-related changes over, in this case, a period of 4 to 6 years. And there is a very loud minority of subjects who do start to show some changes over time. So the real question is, what's different about these people from these people, and what can we do to make sure that we are in this group and not in this group? So with that in mind, we need a model, I think, to help guide us toward answering some scientific questions that can further our progress toward capturing this heterogeneity in aging that someone in the audience pointed out. So, since I'm focusing more on cognition, what's the main driver of cognitive ability? Well, brain structure and brain function. So as we age, as we get older, what are some of the factors that affect brain structure and brain function? Well, there are a lot of things. Genetics is huge. Lifestyle. Sleep is a very big one, and there are clearly age-related changes in how we sleep, and we now are increasingly aware of the fact that the way in which we sleep has an impact on memory function. Epigenetic factors, hormones, they change with age and have an impact on cognition. So there are a multitude of factors here. What I would like to do is focus on just a handful of these. I want to briefly mention protein aggregation. Howie Rosen's going to say a little bit more about this later, and you're going to hear a lot more about it next week. But the neurodegenerative diseases that we worry about and try and fix, things like Alzheimer's disease, Parkinson's disease, Huntington's disease, frontotemporal dementia, these diseases are all associated with abnormal accumulation of misfolded proteins. And we may start to see some very subtle changes in protein aggregation in a population of folks who seem to be aging healthily. So it's very possible that some of the age-related changes we see in an aging cohort is due to protein aggregation. But again, you'll hear more about that later. And I want to focus on two things for the rest of my talk: vascular disease and vascular risk factors, and neural inflammation. And the reason why I want to spend some time talking about these two phenomena is that they are both influenced by lifestyle. So I think that when if we think about vascular disease and inflammation, we have a potential window for interventions that might slow down or influence the changes in brain structure and function. All right. Let's talk about vascular disease and vascular risk. So this is an MRI scan of of a very sort of healthy, community active, normal community-dwelling individual. What happens when you scan a lot of folks over the age of 65 or 70 is, we notice that in about 15 or 20% of this population, there's evidence for a silent stroke. So these folks have had a very, very tiny stroke, and it's never been clinically evident. They're not aware of it, and it seems to be completely asymptomatic. So one of the things we wanted to study is how silent these strokes were. So we took a cohort of folks who were, again, not only intact in their community-dwelling individuals, but their scores on this measure of executive functioning were pretty much average. But you still see a very clear relationship between the number of these tiny little supposedly asymptomatic strokes and how well they performed on a measure of executive functioning. Another thing that we sometimes see on our MRI scans is something that we refer to as white matter signal hyperintensity. So this area here is white matter. You can see this cloudy area around this, and it shouldn't look so cloudy. We much prefer it if that cloud is not there at all. And we usually think that this is associated with some small, subtle changes in the vasculature. And this is a marker of some cerebrovascular change. Does this have an impact on cognition? Well, so one of the things we did is a longitudinal study where we took healthy aging individuals, we followed them over 4 years. We looked at changes in the white matter signal hyperintensity on their scan and divided them up into 4 groups. So We had the first group that had no changes in their white matter signal hyperintensity, these two groups that had minuscule changes in white matter signal hyperintensity, and this group that actually had a noticeable increase in white matter signal hyperintensity, and then ask, do we see any associated changes in executive functioning as a result of these changes in white matter signal hyperintensity? And as you can see here, the groups that had no real clinically significant changes in white matter did pretty well on our executive functioning measures, but the ones with a lot of white matter signal hyperintensity increases are the ones that showed the biggest decrease in executive functioning over that 4-year period. All right, so that's vascular disease. Let's talk a little bit about inflammation. So the neuroinflammation story, I think, is increasingly interesting and of potential importance for our understanding of the mechanisms by which our brains change and our cognitive abilities change. So inflammation is important, right? We need it. It's adaptive. When we injure ourselves, we need to have an inflammatory response to promote healing and to keep us from aggravating the injured region. Well, we're learning now that when there is peripheral inflammation, that there are some things that cross the blood-brain barrier fairly readily and produce some neuroinflammation. Now, neuroinflammation isn't so bad either. It's an inflammatory response that should be transient, should be short-lived, and what should happen is that after a short period of time, your inflammatory response goes back down, and you can go about your day. So it also seems to be the case that as we age, our ability to respond to inflammation and to reduce it spontaneously changes. So certainly in mouse models, we've learned that not only does neuroinflammation persist following even a peripheral injury, but this sustained neuroinflammation is associated with some alteration in brain functioning. So in mouse models where you can do some very detailed microscopic studies, and you don't need their consent to sacrifice them and send them to the autopsy table, what we see is that sustained inflammation seems to affect the hippocampus. And as we know, the hippocampus is very important for memory performance. So one of the things that we wanted to do in our subjects is look at a marker of inflammation. This is something we can get from a blood study, something called C-reactive protein, which I'm sure many of you are familiar with, and has been associated potentially with vascular disease and heart disease. But it's an inflammatory factor. So we measured C-reactive protein in 141 of our subjects, and basically we were able to identify about half of those subjects who had measurable, detectable amounts of CRP in their blood, and about half who did not have any detectable CRP in their blood, and ask, well, do we see any differences in their memory? And again, the hippocampus is very important for our ability to hold on to information over a delay period. So we gave them a list learning task, and during the immediate recall trials, there were really no differences between those two groups. Now, the group in red was the group that did not have any detectable CRP. The group in yellow was the group that did. And again, even though the performances of both groups are still in the average range, what you see is a very significant difference in how well the CRP group was able to hold on information over that delay, really suggesting that the amount of inflammation or neuroinflammation may be one of those many age-related factors that is influencing how our brains are working. We also then looked at the medial temporal lobes to see if that was affected at all by C-reactive protein, and we found again a significant difference with the group with no detectable CRP having significantly larger medial temporal lobes or hippocampal regions, which could then explain some of the differences we're seeing in their memory performance. And then compliments of our colleague across the bay, Bill Jagist, who does very, very fancy imaging to look at the presence of some of these abnormal proteins. Because one of the questions we get asked all the time is, well, does staying mentally active help? And this, again, is a hot topic. It's something that the jury is still out on. Here's a group that obviously values being mentally active. Does it matter? Does it help your brain structure or brain function? So he did some fancy imaging to look at the presence of the protein that we associate with Alzheimer's disease. And it's a busy slide. The part I really want you to look at is just the middle here. The y-axis is the amount of this protein that this Alzheimer's-related protein that the scan was able to pick up. And what we're seeing here is that a group of older community-dwelling adults who showed the least amount of lifetime cognitive activity based on questionnaires was more likely to show some of this Alzheimer protein in the brain than the group that had the greatest amount of mental activity. So I can't vouch for anything being causal, but keep thinking. So, in summary, I think it's pretty clear that aging can have a significant impact on brain structure and function, but the key take-home point is that these changes are neither universal nor are they inevitable, and as Virginia Sturm is going to talk about in a little bit, there are even parts of the brain that do seem to hold up with aging very, very well. I think there are multiple factors that influence how the brain is changing with age. Some of them are under our control. The goal of our aging studies here at the Memory and Aging Center is to better understand what these factors are, how they interact, and how we can influence them to enhance the way in which we age cognitively. Certainly one of the areas in which we age very, very gracefully is in the area of emotion and emotional regulation, and this is something that Virginia Sturm will be talking about next.
So as you just heard from Joel, there are some changes that occur with aging that possibly and at times are associated with decline. So in some people at least, there are cognitive changes and loss of functions like memory and processing speed. There might be physical changes and limitations that occur as we age. Changes in sensation like hearing and vision may get a little bit worse as we get older, and just an increasing problems with our health are often common. So there's a downside that is associated with aging. But given this downside, then why would people be talking about the joys of growing old? What is so great about getting older, and why would life begin after age 46? So I'm here to talk to you a little bit about that side of the story. It turns out that aging really has an upside as well. And the upside is really in this area of emotion. So in the past, we really thought aging was associated with things like social isolation. People's social networks get smaller as we age. You see fewer people. You might not be working anymore and feeling like a productive member of society. You may feel lonely as friends are passing away. You may feel sad and have increasing negative emotion. It turns out that's really not the case. And the modern view is really that aging is associated with increasing levels of social and emotional stability. So we're going to think a little bit more about that. And given this paradox, this apparent paradox that all these areas seem to get worse with age, such as the physical and cognitive areas, then why would emotional well-being improve with age? So I'm going to talk to you first about some laboratory studies of emotion that have been conducted in this area to give you some empirical data about why we believe that emotions improve with age. So the first are some studies that looked at emotional experience. And these kinds of studies often ask people to report on their emotions multiple times during a day, and they're tracked over a week or two. And these studies have found pretty consistently that positive emotional experience increases with age and negative emotional experience decreases. So in this graph, you can see that the 18 to 34-year-olds have the highest levels of negative affect or negative emotion, and it really drops off a lot in the middle ages and kind of stays stable into older age. I should mention, when I'm referring to younger and older people in these studies, generally younger people are in that 18 to 34 range, and older are generally in that 65 and up range. When you ask older adults how satisfied they are with their social relationships, they're often much more satisfied than younger people are. And older adults really report feeling high levels of happiness and other positive emotions when they're spending time with close friends and close family members. much higher levels than even the younger adults. So in this study, they looked at a simple, basic attentional bias that they see in older adults. So what they did was they had a person sitting at a computer screen, and they flashed two faces, a neutral face and an emotional face. The emotional face could be positive or negative. And then the faces disappeared, and a dot appeared on one side of the screen. And all the subject had to do was respond on the keyboard as to which side the dot was on, as fast as they could. And they found that the older adults were much faster when the dot was on the side of the positive face, and they were much slower when the dot was on the side of the negative face. The younger subjects, you see, don't really have a bias. They responded about the same speed in both conditions. So what this study suggested was that the older adults, at a very rapid automatic level, were just attending more to the positive face so that they could respond to that dot more quickly, and they were kind of avoiding that negative face. So they were a little slower to press the button when the dot was on the same side as the negative face. On tests of memory, older adults have this better recall for positive information. So on that task that I just told you about with the faces, they also did a condition where they asked people to recognize the faces that they had seen during the task. And again, older adults remembered more of the positive faces than they did the negative, which makes sense because they were attending to them more. When you ask them to recall different memories from their lives, older adults also recount even negative memories less negatively and more positively than younger adults did. But it's not all a rosy story here for the older adults, because once an emotion has begun, and in particular a negative emotion, there's some evidence that older adults might actually have longer and prolonged activation to negative stimuli, so more like physiological arousal to a negative event once it's actually taken place. And there's some thought that this might be because they have less flexible cardiovascular system and they're not as good at regulating those emotions. So again, given this high reactivity to negative stimuli and negative emotion, then why are there these increasing levels of positive emotion in older adults? So to understand that question, we need to understand a little bit more about emotion and the anatomy of an emotion. So I'm going to take you through a background of some basic knowledge that we have about emotions. And emotion research is kind of becoming more and more popular these days. But, and it hasn't actually a long history. So at the time, in the times of Plato and Aristotle, they talked about the passions, and William James talked about emotions. Darwin discussed the emotional expressions in animals and humans. And more modern thinkers, Paul Ekman, who was here at UCSF, who did a lot of studies on facial expression, Bob Levinson at Berkeley, they've all been thinking about emotions and how to measure them, because we all know what emotions feel like, but they can be hard to pin down in a laboratory and hard to define. So one helpful definition that I often refer to is one from Levinson when he describes emotions as short-lived phenomena. And by short, he means really short, like 3 to 5 seconds is what the general thinking is about emotions. And you might think, my emotions are longer than 3 to 5 seconds, and that's probably true. But the thinking about it is that there's little pulses of emotion that occur over and over again. So if you feel sadness, for instance, for a long amount of time, it's these small bursts of sadness that occur over and over again. And emotions really have two basic components. So they have a psychological component and they have a physiological component. So psychologically, when we have an emotion, we shift our attention, we might have certain thoughts, we might remember certain things that are relevant to the situation. Certain actions and behaviors might become more automatic. And physiologically, emotions really serve to harness different systems in the body and orchestrate them together to effectively cope with some stimulus in the environment that needs our attention. So some examples of these are the autonomic nervous system. Blood flows to certain muscles, for instance, if we need to run away. And our facial expression is another important piece, which I'll talk about more. So why do we have emotions? It's really thought that emotions have evolved to serve different kinds of functions. And there are two kinds of functions that they serve. There's intrapersonal functions of emotions and interpersonal functions. So intrapersonal functions are really the subjective experience that accompanies an emotion. So when we feel an emotion like disgust, we know what that feels as an internal visceral sensation. And interpersonally, when we feel disgust, we might signal it on our face. It might signal to someone else in the environment that they need to help us out in a certain way, or that they too should feel disgusted because something in the environment. So for that example, for instance, if you see something generally appetizing in the environment, like maybe a piece of pumpkin pie, and you notice there's some flies on it, you may wrinkle your nose, feel your lips kind of curling up, feel your tongue moving forward in your mouth, and you'd feel disgusted. If you see something threatening in the environment, like someone with a gun, for instance, you may raise your eyebrows and spread your lips and feel afraid. Or if you see something tragic, some kind of loss, like a car accident, you may feel your corners of your mouth turning down and your eyebrows moving up and in, and you might feel sad. So to look at some positive emotions are a little bit different from negative emotions. So we don't feel positive emotions when there's some threatening thing in our environment or something disgusting, but really positive emotions are thought to function to serve to bring us closer to other people. We feel more creative when we have positive emotions. We approach others more, and we kind of foster these social relationships more when we're feeling positively. So a few examples again, if you see something repetitive like an ice cream cone, you may feel happiness or content. If you see something kind of funny in the environment that's unexpected, you may laugh and feel amused. And if you've accomplished something that you might not have thought you could accomplish, or that you feel others would be impressed by, you may throw your shoulders back and puff up your chest and feel proud. And pride is really thought to signal to others that you're an important group member, that you have talents, and that are important for the group to notice. So as I mentioned, emotions unfold over time. And I'm going to walk you through how this occurs. And again, in just that rapid 3 to 5 seconds of an emotion. So if we could kind of slow down an emotion and look at it frame by frame, this is what it would look like. First, we have our appraisal. So something happens in the environment. We have to rapidly judge it, make a decision. Then we have a rapid emotional response tendency. So you can think of this as the beginning of an emotion that happens really quickly, kind of unbidden. And this unfolds into a full-blown emotional reaction. So it might seem like there's no flexibility in this system because these things happen automatically, we don't have any control. But that's not necessarily the case, because there's a little bit of wiggle room in the system. So you can change the emotions that you're having in several ways. The first is by reappraising, or by changing the way that you think about the situation. The second is a little later down the pipeline is suppression generally. You can hide on your face what you're feeling. So if you're really feeling sad, you may mask it and look neutral. Or you can amplify, well, you wouldn't amplify sadness, but you could substitute. So if you felt sad, you could pretend that you feel happy by smiling. And for amplification, it's more for the positive emotions. So say someone told a joke and you thought it was sort of funny, you could laugh more than you might have actually felt. If you're really savvy at regulating your emotions, you can actually divert this whole process from happening and avoid the whole situation, say in the context of negative emotions. So I could choose a different situation to be in. I could modify my environment so as to not have to look at whatever stimulus is in my environment that I don't want to see, for example. Or I could deploy my attention otherwise and kind of focus on certain aspects of it that I find less aversive. So I wanted to walk you through an example. So let's pretend that we're taking a walk at night. And we decide to walk through the park, and there's some trees. And we see a shadow in the corner of our eye, and we hear some of the leaves kind of crunching. We may feel our heart rate immediately quicken. We may take a deeper breath, look around. And this may emerge into a full-blown emotional reaction of fear. So we may, our eyes may get wide, and our mouth may, our lips may spread a little bit. But we also could stop and, change those emotions that we're having. So we could think, wait a minute, maybe there's not, a person in that bush in that dark corner, but maybe it's just a friendly cat and nothing to worry about. Again, we could suppress how we're feeling. So in case there were someone looking at us, we could just pretend everything's cool and we feel no emotion at all. And again, if we're particularly good at regulating our emotions, we could avoid this walk altogether. We could take a different path that perhaps is more, better lit, or we could change what we're thinking about and focus on what a beautiful night it is and the stars and not worry about the sound. So again, as it has been alluded to several times, these emotion regulation strategies, that kind of bottom level of the process model, seem to get better with age. Older adults really feel and report that they have better control over their emotions than younger adults. They feel like they are better at regulating which emotions that they have and when they have them. Older adults are also better at positively reappraising. So the example for positive reappraisal, again, is that cat example. So they're able to think, oh, it's probably nothing, or in a different context, just thinking about the positive aspects of the situation and rather than focusing on the negative. Detached reappraisal is kind of just avoiding the emotional parts of the situation in general. They're not so good at that. They do engage with emotions. It's not like they don't have any emotions, but they really tend to focus, again, their attention on the positive aspects. Older adults are also better at, again, avoiding situations where they know that they'll have negative emotions. In some situations of conflict, for instance, they may just do more passive strategies of avoidance rather than engaging and having interpersonal strife. They may just, change the topic and focus on more positive aspects of their relationship. And there's a lot of data and a really important theory out there called the socio-emotional selectivity theory that really posits that older adults prioritize emotional goals and really prioritize emotion regulation. And they really choose to have as many positive emotions as they can and minimize as many negative emotions as they can. And the thinking about this is that as we get older, our time perspective changes. And we really, as our time on Earth kind of gets shorter, that we want to spend time with people who are closer to us, like family members and close friends, as opposed to meeting new people and having new experiences, which is more common when we're younger. So really, when we think about what this emotional wisdom is that occurs in aging, it really seems that older adults are better at these first two parts of this model. So as I mentioned, they're good at avoiding and choosing situations where they know they'll have positive emotions and not negative emotions. They're good at reappraising and thinking positively about situations rather than negatively. And as Kate Rankin told you about last week, emotions also are related to the brain. And she told you about these two different networks in the brain. One was the salience network over here in the red, and the other was the executive control network in the blue. And the salience network really has to do with these emotional processing systems. And as Joel mentioned, there's some evidence that the structures in this system are preserved with aging, as opposed to the changes that are more common in the executive control network. So really this area is an area of a lot of research, and we don't have a lot of answers about specifically how emotions and what part of emotions, when you're precise about defining which aspect of emotion you're studying, relate to this network. So you could think about emotional reactivity being related to this network, how much you react physiologically or behaviorally to stimuli. You could think about emotion regulation and how you can change those emotions that you're having and how that relates to this network. So there's a lot of work to be done, and it's really kind of in its infancy. So again, just to summarize, the good news is that really emotional well-being gets better as we age. People experience stability in their emotional lives, and despite the changes that might seem bad, like smaller social networks and these cognitive and physical changes, older adults really feel much happier as they age. And we think this is really because of kind of low-level attentional biases to positive stimuli, the skillful, kind of wise choice of selecting situations where you'll feel certain emotions, positive emotions, and not negative ones. And really, again, this ability to see the silver lining in the clouds and to think of things in a positive light. And now I'm going to turn it over to Howie Rosen to tell you about mild cognitive impairment.
So to really segue from Virginia's talk to my own and Joel's before that, what we've been talking about up till now is things that we think are associated with aging that affects most people and that we think of as normal aging. But one of the things that we recognize is that not all of aging is associated with only normal phenomena, but rather that aging puts us at risk for diseases, some of which can affect our thinking. And we have to deal with that too, and especially as clinicians, people who see individuals in the clinic, we have to recognize that problem and figure out how to deal with it. So I'm going to jump for a moment to talk about this term dementia, which I think people consider understandably a scary term and not something we want to talk about, and yet I think it's a good touchstone for the beginning of this talk. So dementia really is a very specific term that we use in clinic, which is just a one-word description. And what it says is that it's the recognition that somebody has had a progressive decline in their thinking, which has lasted over at least a few months, and the problem's been getting worse. Often it's more than a few months by the time people get to see a physician about it. And that now it's having major effects on their ability to get along in everyday life. Things like maintaining their finances, cooking, shopping, and eventually, years down the road, it can affect even more basic functions like dressing and bathing. I'm sure many people are familiar with this phenomenon through lots of different venues, possibly personal experience, certainly through books and movies, etc. So this is a phenomenon that we have to deal with. And when the problem gets that bad, and the reason the term dementia is important for us as clinicians is that it signifies that there's probably a disease going on in the brain. Once upon a time, 30 years ago, certainly, we used to think that that kind of cognitive trouble was a normal part of aging as well. And the term senility is really from that era that says, well, this is just part of that. And words like dotage and all these things really imply that this is part of normal aging. But now we recognize when the problem gets that severe, it signifies a disease. So how do we approach the fact that unfortunately, this disease is all too common, and we recognize that it's there. So I think the approach that we take in the clinic is vigilance and awareness. And what we're trying to do is improve our ability to recognize that process as early as possible so that we can treat it as early as possible and avoid it altogether. And so that's really what I'll be talking about, is that set of questions and how we're trying to deal with that question. So for aging researchers, one of the main questions, a main question, not the main question, is how do we recognize cognitive trouble or thinking trouble that's not due to normal aging, and how do we recognize it early, of course, as early as possible? And it turns out that the answer to that question comes from our ability, which is good in some cases and still developing in others, but our ability to recognize the signature of a specific brain disease and how it's affecting the brain. And it turns out that how we recognize that is because you could think of the diseases as affecting the whole brain at once. Just imagine the whole brain and it's all affected by disease all at once, and that's one model of the brain. But you learn that there are many systems in the brain, these memory systems and executive function systems and emotion systems, and it turns out that now that we understand that there are all these different systems, it turns out they're not all affected by diseases at the same time, but rather, for reasons we really don't understand, certain diseases have a selectivity where they tend to involve certain systems very early, and only later on do they start to involve the other systems. So some people, many term that selective vulnerability, that a certain pathological process that's injuring the brain is only affecting a certain system early on. So what we're trying to do is recognize those early effects in certain systems, and then we try to infer from that what's happening to the brain. So that's the overarching theme, and I think that theme is going to apply well beyond Alzheimer's disease, but Alzheimer's is the best model for this process, and it's also probably the most common of any of these diseases that affects thinking. So this was mentioned briefly in our first talk, and just to review, if somebody had Alzheimer's disease and they were able and willing to donate their brain so that we could look at it after they passed away, what we would see in the brain is these two basic kinds of abnormal findings, only microscopically small. They can't be seen during life in any way right now, and they're called plaques and tangles. The plaques are accumulations of abnormal proteins that are sort of outside the neurons in this sort of surrounding space, and they're just a big glob that stains with certain chemicals, and we say, oh, that's a plaque. Then there are these other things called tangles, which really are the nerve cells being all shriveled up and being filled up with a different kind of protein. You don't have to know the names, but the proteins that are in the plaques are called beta amyloid. I'm sure many people have heard something about that. And the proteins that are in the tangles are called tau. And it turns out it's relevant to understand these two processes to know what's happening in the brain. So there are these plaques and tangles. And as I said, if you looked at somebody's brain who had Alzheimer's disease, you would see them all over the brain. So how is it that these small microscopic changes that affect the whole brain really cause very unique problems that we could recognize early and affect a specific system? How does that happen? So it turns out that the model for our understanding of this whole area of selective vulnerability really comes from pioneering work that still affects our thinking today by these two pathologists called Brock and Brock. And they were pathologists, so they habitually analyzed brains after people died for many reasons. And they had a brain bank. And they started to recognize and reason that, you know, if Alzheimer's disease spreads through the brain with this idea that it starts in one place and then it starts to involve more places and more places, maybe since we see Alzheimer's quite frequently, maybe if we go back and look at all our brains, we could detect that pattern. So that the hypothesis was, if we see any Alzheimer's, we'll always see it in one place first. And then if there's more of it, we'll see it in that place plus other places. And if there's more of it, we'll so on and so on. So that was the idea that they went in with. And that would help them to understand, and all of us to understand, how this problem tracks through the brain. So it turns out that they, of course, I wouldn't be telling you about it if they didn't have very meaningful findings. And it turns out that that the relevant structure turns out to be the hippocampus, that's been mentioned many times, and its related structures. So just to remind us what the hippocampus has been mentioned many times, only because it's so important. So this is the structure. I think HM was mentioned at the last meeting. HM was a famous patient who unfortunately had to have his hippocampi removed because he had seizures, and the surgery worked for the seizures, but it left him with this profound memory problem where he could not make new memories. And he was the first patient who taught us how important the hippocampus was for memory. This is also the structure that Dr. Kramer mentioned, which shrinks a little bit with aging. And so the question is, what happens in Alzheimer's disease, this hippocampus structure? Why am I bringing it up? So the images that I'll show you next from Brock and Brock's study are a close-up of this region. So this is this is from a brain image. So if you were cutting through the brain like this, in this kind of orientation, and you sort of moved apart the front part, and you looked at the kind of about at this level in the brain, and you sort of looked at the surface, so you'd be seeing the hippocampus. And we're going to show close-ups from the Brock and Brock study of that region. And so what they found is that the pattern was with the tangles. The plaque, the stuff that was outside the nerve cells, those globs, didn't have as nice and clean and discernible a pattern. But what they found is that there was a very nice pattern with tangles, and if they saw any tangles, they saw it in this region right here, which is called the entorhinal cortex. Again, I wouldn't want you to know the name, but that's the gateway to the hippocampus. It's the little structure through which the whole rest of the brain sends all its information to that structure, and then the next stop is the hippocampus. So if they saw any changes in the brain, they saw these little tangles right in this entorhinal cortex. If they saw a little bit more, and the rest of the brain was fine, they didn't see any other tangles. And then when they looked at patients who seemed to have a bit more, they had more changes in their entorhinal cortex. So that's right here in this part of the brain. And then they started to see changes in the hippocampus itself. And that's up here. And that's what these little black dots represent, is their impression, a representation of how many tangles they saw. Then as the process got further, they saw more tangles in both the hippocampus and the entorhinal cortex, and the process increased. And when they started to look at other parts of the brain, they started to see these tangles spreading in other parts of the brain too. And then, of course, they had very late stages where they saw really a lot of this all over the place. So what they also noticed is, they were pathologists. They didn't really meet any of these patients during life, so they didn't do a very thorough assessment. But they did look back and try to decide, well, in life, were any of these patients recognized to have a significant cognitive problem or not? And it turns out there was a rough relationship between how much of these tangles they saw and the cognitive problem. So in those, what they called stages 1 and 2, where there was just a little involvement of the tangles, nobody had noticed that the patients were demented. It had dementia. It doesn't mean they had no cognitive problems, but they weren't bad enough that they came to the attention of an average physician who might have seen them. Then in the middle stages, about half did and half didn't, so suggesting more of a relationship. And then everybody who had this kind of extensive change with tangles all over, all had been recognized to have dementia. So what they were then showing is these changes that we're seeing after people die are clearly relevant to what we saw during life, because there's a relationship between how much of this and how much this has spread through the brain and what people had during life. And this study has become our model for trying to understand what's happening in diseases like Alzheimer's. So to summarize what they found, which still is our template, is that in Alzheimer's disease, the main effects start in that hippocampus and structures right next to it that supply information to it. That the effects in the brain track best with those tangles and not the plaques. And those tangles are in nerve cells, so it really makes sense that the pathology that you see specifically in the nerve cells, which do all the work in the brain of thinking and transmitting information, so to speak, that they would be in those structures rather than hanging around outside the nerve cells. And based on what they could see, that kind of tracking of these tangles through the brain has the closest relationship to thinking. And roughly, that's really what's borne out as we've continued to study that. And somewhere in the middle of this process, from those very earliest phases in that stage 1 and stage 2, until the process is really well developed, that's somewhere in the middle. They kind of said, well, it must be that thinking trouble starts in that somewhere in the middle of that process. And that model has really influenced how we approach studying patients who are alive and with us and might have thinking trouble. And because of these kinds of results and because of our knowledge of how important the hippocampus is in memory, we spend a lot of time looking at the hippocampus. And one example, probably the most frequent example of how we study the hippocampus, is we measure its size. And it's really not that hard to do. You get images like I've been showing you, and each image is just one slice, but if you go through the brain like this and you do the area on one slice and the area on the slice behind it and the area until you say, I'm no longer in the hippocampus because I know my anatomy, and you add all those areas up, you get a volume, and that's how big the hippocampus is. And here you could see that in person A on the right, that the hippocampus is kind of small, again, assuming all the areas in the back of the front are similar to what I'm showing you, and that in person B, the hippocampus is bigger, and that's the kind of data you would get. And so it turns out that if you look at a cross-section, sort of patients with severe memory problems versus patients who seem to have same age but have fewer memory problems, that the hippocampus is smaller in the patients who have all these memory problems. And actually, the work I'm showing you is not just looking at it at an individual time point, but this is studying people over time. So they're looking at what's going on in the region of the hippocampus over a period of about a year and saying how much change or loss of size of the hippocampus is there in just 1 year. And there's significant change. So, and it's bigger in the Alzheimer's group, the patients who we know have this very severe memory problem I've been talking about, and the cognitively normal age-matched controls. So the model that I think we've tried to develop from this and that really informs what we think is happening is there's a model that I think Dr. Kramer was telling you about, where as you get older, you start to have, you're doing okay. And then there are some subtle changes in memory, and he told you a lot about the kinds of things that are affecting that. But you're always above the line, so to speak. In other words, nobody would consider your memory impaired in the sense that you're much worse than the average person your age. But within that, as he said, there's a lot of variability. On the other hand, if biochemical problems, for instance, those related to Alzheimer's, and we'll be talking about that in subsequent lectures about what those changes are, if they accumulate, at some point they start to affect the nerve cells so that they start to accumulate these tangles. And at some point, before it's probably noticed, these tangles start to accumulate, and eventually they grow and they spread into various parts of the brain beyond just that entorhinal cortex and hippocampus. And you start to develop thinking trouble, and it starts out kind of mild, and you're not really sure if it's normal or not, but at some point it really gets to the point where it does affect your memory a lot. But even then, you may not develop such a bad problem that we would call it dementia. And so this area where you're sort of developing problems that might be measurable and where the hippocampus has changed size and all that is really the focus of a lot of research, because this is a state where we already recognize there's probably a problem set in. It's really an important time that we want to intervene and try to use medicines, etc. And it turns out that this mild impairment is not just, it sounds like a very generic term, but it's really become a term of art and a very specific term for this state. And so when you read about memory loss, you'll often run into this term called mild cognitive impairment. And again, although it sounds generic, it really refers to this very specific state where you have cognitive complaints and you're feeling like your memory is not as good as other people your age. Your family might be noticing it too, or your friends, and you're starting to compensate. Even though you always were a good person who wrote things down, now you're doing a little more. You feel more dependent on your notes than you did. And you feel like it's maybe speeding up a little and it's worrying you, but you're still able to do all the things that you normally do. You pay your own bills, you're shopping, you're cooking, you're holding your own, but you're noticing things. And that's what people mean by mild cognitive impairment, that you don't have dementia, but that you do have these significant memory changes, which you and people who know you feel are a little more than they should be, because we all know what aging we think looks like. So can we recognize that in the clinic? So it turns out we can recognize it pretty well. And a great example is this workhorse test that comes up over and over again when we talk about memory, is this list learning task. So this is a task where we give you a bunch of words to remember, and I would read the words to you, and then you would have to repeat them back right away, and then I try it again. Okay, let's do that list again. And so you could imagine if I give you the list 4 times, you might start out remembering a couple, but then you'd get those in, and then you'd remember 2 more. And at some point, you can maybe remember all the words, or certainly more than you start out with. So that's the repetition phase. And you're encoding, as was mentioned in that first lecture. You're getting the information into your memory. And then we distract you with some other tasks, and then we come back 10 or 20 minutes later, depending on the task, and we say, hey, by the way, remember those words I asked you to try to remember? Can you tell me some of them? And so it turns out that there's quite a dramatic pattern when you have this hippocampal region injured that I won't show you, but you'll hear. So remember, this is a 9-item list, and you're going to listen to a patient who has heard that list 4 times and is now repeating it on that last try.
Peaches, lemons, cherries, belt, hat,
Wrench, he gets wrench too. And then after, so it turns out it's about 6. It's 6 words, which is not bad. And then when we ask him 10 minutes later to remember the words.
A few minutes ago, I read a list of words to you several times. Tell me all the words you can remember on that list.
Wrench. Grapes. Orange.
So it's only a couple that he ends up picking up from that list. And that we call rapid forgetting for understandable reasons. And it turns out that what I want you to focus on is this. So this is a graph of many people taking this kind of test, that where in the controls, the number of words remembered goes up as they learn the list better and better. And then after that delay, they don't lose very many. And in Alzheimer's, as the comparison where we're very clear people have these significant memory problems, the learning is the same slope, although the total number may not be remembered. But the dramatic thing is that after that time, many of the words originally remembered are lost. And the slope or the pattern in these patients with mild cognitive impairment who have these kinds of memory complaints I'm talking about is closer to the Alzheimer's type slope than the control slope. And it turns out that when you look at patients' hippocampi, for instance, with this mild cognitive impairment, that the changes are slightly less in degree, but similar to what we see in Alzheimer's disease, where the hippocampus is shrinking faster in mild cognitive impairment than in controls, although not yet as fast as Alzheimer's disease. So, and it turns out that people with this kind of pattern, with these kinds of complaints where they and their family are noticing things and where they have this specific kind of impairment on the memory testing that we see in clinic, that they are worrisome, that many of those patients do end up over subsequent years usually showing that they have Alzheimer's by getting worse, and we can now demonstrate that with markers of disease. And the imaging work that I've been showing is adding to our ability to characterize that problem. And of course, this mild cognitive impairment then is a very important time period for us to intervene as best we can. And as we develop new treatments, hopefully, over time, this will be a critical time period to study those treatments and also to treat people. And I think that the message I want you to hear is that that kind of memory change that I've been showing you is not what Dr. Kramer described for you in normal aging. It's certainly the emotional things is not what we're testing here. These are problems that really don't look, at least in this stage, like people who seem to be aging normally. They're recognizable, and the reason they're recognizable is because they really show us how some process, usually Alzheimer's disease, is involving the hippocampus in a very specific way. Now, of course, that's just the beginning of this story. We've kind of recognized now how to find this problem and how to characterize it at this stage. But what we really want to do is try to diagnose things either earlier. So I think the next phase of our research is trying to bring that recognition of this problem back a year or 2 years or 3 years. And as you can imagine and see here, you know, the cognitive testing may be more subtle, maybe it may be more difficult to recognize and to compare with aging, but maybe some of the imaging data or other kinds of things will help us to characterize this process in a way that says we could see the signature. Even though the memory test may not be quite as bad, we can see the signature of this process affecting that system. And there are other frontiers that we have to deal with. Of course, even though I said this mild cognitive impairment is a worrisome situation, not all patients do end up getting worse and developing dementia. So there are two ways to think of that. One is, well, maybe they don't have Alzheimer's. They might have some other kind of problem that caused them to have these memory problems but isn't going to get worse. Or maybe for some reason they do have this problem but they're protected in some way. And it could be that some of the factors that Dr. Kramer mentioned or other factors are a combatant against these kinds of changes and that you can resist them for much longer. And of course, not all dementias, as it turns out, are due to Alzheimer's. There are other things, some of which we'll tell you about. And they all involve the brain differently. That the system that I talked about is very vulnerable to Alzheimer's disease, but other systems of the brain are vulnerable to different diseases. So when we think about those diseases, the MCI, the early problem syndrome, is going to look different. And we're still trying to figure out what that syndrome looks like in other kinds of diseases, how to recognize it, and how to develop tests that we can use, quantify, that can tell us we're in that phase and we have to be aggressive in a person like this. And these are really areas of current research, is to focus on those aspects of mild cognitive impairment. So the message really then is that the kind of memory impairment that's caused by diseases like Alzheimer's is not just different in degree, but it seems to be different in kind than the kinds of cognitive trouble that we see in what we think is normal aging. And the reason it's different in kind is because these diseases have a real predilection to affect certain systems, and those systems show a lot of trouble when the rest of the brain is doing okay. And the good thing about all the testing that we've done over the years is the tests are pretty well developed to try to recognize those problems when they're developing and to pick up that signature. But the challenge we have is to develop new tests that are even more sensitive in earlier phases and are sensitive to problems where different systems are involved besides the hippocampus. So that's, I think, the message that I want to give you is how we try to deal with this in clinic. And the nature of our vigilance is really to think about the brain in these terms. So thanks.
Yeah, so I want to thank all three speakers. For me, who've been in this field for quite some time, hearing them, I always learn new, so thank you. And I think we have lots of time for questions. Speakers can come on up and maybe repeat the questions for the television, huh? Okay. Yes, sir.
Which is a great question. As I mentioned, the fact that this period where you're above the line or starting to get below the line, developing memory problems, is a period where we would want to intervene with medications. And the gentleman was asking, what medications? And these, I think, are medications that are currently under development. So what the medications that we're currently developing are trying to interfere with some of these biochemical processes that I highlighted but didn't talk about too much. They relate a lot to the beta amyloid that fills up the plaques, and they also, some of the medicines are trying to untangle the tangles, so to speak, or prevent them from forming. Most of those medicines are in one of two stages. They're either in the stage where they're one of three stages, either in cellular models where they're just trying to, in the bench, just figure out how they're working. Some of them have been used in animal models that try to replicate this process and mimic it, and they've even worked in that setting. And now some of those drugs are now moved into the clinical arena where we're trying them out on people with memory problems like this. You've probably read about some of these drugs that haven't hit yet, and then people argue about the reasons why that particular drug that seemed like it would work and that did work in mice didn't work in people. But there are many drugs that really affect those biochemical processes. So unfortunately, I can't point to the one that we currently use in clinic, but there are many, hundreds literally, that are currently under development, and many of them at the kind of clinical trial stage. I think that what's important about highlighting this period is it's obviously relatively early from the perspective of the worst problems haven't set in yet. And it's really important when you're detecting and feeling like you may be developing this kind of problem to talk to you about to your physician about it, because once in a while we discover some metabolic problem that isn't Alzheimer's disease. It's a thyroid problem or B12 deficiency, and the truth is maybe at the memory center we could probably, without doing any tests, figure out if that's really your problem or not. But out in the community, I think a lot of memory problems sound the same to people, and so if you're developing memory problems, it may turn out to be a problem that at least without doing this fancy testing, looks like it's the same as the changes I'm talking about, but it turns out not to be, and that some other treatment is appropriate. So always best to talk to a physician about it if you're feeling this way, earlier rather than later.
I might just make one comment, too. And, I mean, we do an awful lot of reassuring of people. There are many reasons why people have complaints that are not Alzheimer's disease, and, you know, I think if you are overly self-vigilant, I think that you may come to us with convinced that you have Alzheimer's disease, and when you leave, we're convinced that you don't, and I think it's our job to tell you that. So, you know, but I do think that we consider, you know, any symptoms that you have as you get older as potential warning signs that should be looked at in a very serious, not in a cursory way.
On ginseng, not ginkgo. Okay. You know, I'll also defer to Dr. Miller, who I think has a breadth of experience that sometimes doesn't encompass mine doesn't encompass every study. I think my general answer for many questions. So again, to repeat the question, the gentleman was asking about, he was commenting that ginkgo has been shown by several studies, most showing that it really doesn't have a beneficial effect in protecting memory. And he wondered, accepted that, but wondered about other compounds like ginseng. And I think my general answer is that for most of these compounds, the definitive study to figure this out often hasn't been done. I think in a lot of studies, we only have to take the evidence-based approach, and ginseng is one of those studies. So I think the evidence supporting ginseng, a lot of it comes from population-based studies and who eats what, and there are many issues that need to be sorted out, as you know. In the smallest studies that have tried to use ginseng to combat memory problems, it hasn't really been effective, but you could argue that maybe those studies weren't large enough or that they were treating the wrong thing. The more we can characterize the memory problem and sort of specify this is the problem we're dealing with, if it's an Alzheimer-type memory problem, will ginseng help versus if it's another kind of memory problem. It could be that ginseng might have impacts on some of the inflammatory processes that Dr. Kramer, but once you're dealing with Alzheimer's, it may not work anymore, or it may work very early in that process, but not later. So, without remembering, to be honest, every specific study relating to ginseng, my general answer is a lot of the studies that would really sort out whether it could be helpful haven't been done yet. So
maybe, so possibly.
Absolutely possibly. It's more a matter of when and where. Absolutely possible. Yeah. It's a matter of where and when, rather than no or yes, I think. Did you want to?
Well, no, that's the perfect answer. Absolutely possible. I think that's right. You're going to get all of our sort of, takes on what is, really promising. But I think there's, across our center, a real sense of enthusiasm before the studies started coming up about exercise in the brain. You'll hear more about this throughout the course, but you're looking at a bunch of exercisers, except Virginia. I think she's too young yet, maybe, but she will. And I think the data coming out on that is really good. I think this is something that we almost routinely recommend. There's so many reasons why exercise is good for the brain, and I think the data is starting to show that, too.
So the question was, are mental activities or non-physical activities like meditation and crossword puzzles, are they beneficial as well? I think the general answer, and I think Dr. Kramer really should talk about it, since he addressed it, is yes, with a qualification.
Yes, with a qualification. Right, yeah. I think that we don't know a whole lot about the impact of meditation and crossword puzzles on cognition. The epidemiological studies that tend to hint that there's a beneficial effect are fundamentally flawed and don't really answer the question. We're only just now, and I guess there are two separate issues here. Does meditation and mental exercise enhance typical aging, or is there any chance that it can either prevent or minimize the impact of a neurodegenerative disease like Alzheimer's? And we don't know the answer to either one, but we're just starting to see some reasonable studies that you are using sort of random controlled trials and put people into a mentally active group and a couch potato group. But I don't think you need to have empirical evidence to support the concept of staying mentally active.
I guess, the qualification that I wanted to add, that I think even the epidemiological data doesn't support the idea that one particular activity is more beneficial than another. And I think that that's the issue we're wrestling with. There is a lot of hope and attempts to sort of show if you do this task, whether it's crossword puzzles or computer programs or whatever, Nintendo makes one, that these things are the key to this process. And what I think we know so far is that mental activity in general, which might include meditation, is generally beneficial, and it's mostly, as Joel said, based on epidemiological data, which says that people who who do that more seem to retain their thinking abilities as they grow older better than people who don't. And of course, there are all the cross-section and non-controlled aspects of a study like that make conclusions about causality difficult. But what I don't want to discourage people from thinking is, I'm doing the wrong mental exercise, that all the classes I take are worthless and I should buy a Nintendo or vice versa. I think that social activity is important, physical activity, and for most of us, I think we don't stress the physical activities enough. So that's the qualification I wanted to convey, is there really is very little data pointing to a specific mental activity, just that it's good. So I think Dr. Kramer's early comment that you're all here is actually very relevant. Despite everything else he said not being.
The question was about depression in aging, because I was discussing the effects of emotional well-being in aging. And, I don't know the rates of depression in aging and whether they change. Do you know? Yeah.
I think just supporting Virginia's, talk tonight, depression does not really particularly get much higher in later life than middle life, and it's actually highest, as you might have guessed from her early graph, earlier in life. So this is, a myth that as we get older, we tend to get more depressed. In fact, not the case at all. Yeah. But treating it, I think, is critically important, and I think great data suggests if you have a mood disorder and it goes untreated, that it has huge implications for health in general and probably for cognitive health as well. So.
Yeah, definitely depression is a risk factor for cognitive problems and converting to Alzheimer's disease from that mild cognitive impairment range, so important to treat it. Okay, so the question has to do with the role of thought in emotion and how changes in thought might impact emotion with age.
What's the relationship between thought and emotion?
The relationship between thought and emotion just generally. So that's a great question, and we could talk about it for a long time. The short answer is yes, thought is definitely involved, and there's, cognition, emotion interactions are a huge area of research, how emotions influence decisions, those speeded reaction time tasks, things like that. But thought has a role in that whole process of emotion that I described, from how I judge a stimulus in my environment, my first, immediate gut, reaction and thoughts about it, and also later in the process as I that cycle kind of keeps going over and over. So I have my first thought, and then I think more about it, and I might change the way I'm thinking about it. And again, as I described, those changes in how we think really influence the course of the emotion, how it unfolds. Does that answer your question?
You might say a word about cognitive behavioral therapy.
Yeah, and so there's a really effective kinds of therapy in this area called cognitive behavioral therapy that's some of you may have heard of. It's a kind of psychological intervention where people really look at the relationship between thoughts and moods or emotions and behavior. And really the thinking is that by changing our thoughts, we change our moods and feelings and our behavior. And if you tinker with any part of that system, the other two kind of move with it. So thoughts are really, really powerful and manipulatable part of the system.
So the question is there a sort of normal rate of loss of memory over time with, so I think I'd like to get rid of the word normal aging and instead use the term typical aging. Now, what happens with aging in the absence of disease is maybe one way to frame the question. And if there's an absence of any of these neurodegenerative diseases, if there's an absence of cerebrovascular disease, if there's the absence, or you're able to modulate any hormonal changes, there's no inflammation, their sleep is good, all of these other things are really hunky-dory, then I think that the age-related changes in things like memory will be minimal. But that's a hypothesis that we're trying to test. So great question. The question is, how did we control for how long C-reactive protein was elevated and measurable in our sample? And the answer is we didn't. It was a cross-sectional study. It was an initial foray into trying to understand the relationship between neuroinflammation and brain structure and cognition. And some of these great questions like the one you just posed will only really be addressable by longitudinal studies. And we're launching these now. Okay, so there's a great question on the age-related changes in quality and quantity of sleep and what impact that has on the aging process. And I will be the first to admit I am no expert on sleep, so I will be happily defer to Dr. Miller on this one.
But could you comment on what you meant when you said the way one sleeps?
Great. So sleep, the way we sleep, what does this mean in terms of how we age? So I think this is becoming one of the hottest areas in all of research related to aging. Christine Yaffe here at UCSF is doing a study of women who she has sleep data for over 20 years. It's called the Pittsburgh Study of Aging. And I think that she has really good data and people who have been studied in the sleep laboratory to suggest that the women as a group who have disrupted sleep have not as good cognitive aging. So I think there are lots of correlative studies that are beginning to emerge that suggest bad sleep is bad for the brain. We know a lot more about certain sleep disorders, like something called sleep apnea. And no doubt about it, sleep apnea, which is manifested in the bed by loud snoring and sudden stops in breathing, is terrible for health. It increases hypertension, increases cognitive deficits. Not clear it's a risk for Alzheimer's disease, but it's certainly something that causes bad cognition in patients we see in our clinic that can really be treated. And then also we're learning that certain sleep patterns are predictors of Parkinson's disease. And something that is called REM behavior disorder, where someone during dream state doesn't turn off the motor system, so they actually act out their dreams. This can be a prodrome, not always, but can be a prodrome for Parkinson's disease. So I think huge amount of research going into sleep right now, and also one of the people from the audience kindly supplied us with a nice article about, I think, hamsters. And it's true, we know that when you are in REM sleep, that you are consolidating your memories. We've learned this from animal research, and so not having REM sleep interferes with your ability to remember. Yeah, go ahead.
I was going to say, I was going to refer to that work, but from the human standpoint, there's psychological research which indicates that memory improves after a night of sleep, and that even more than just the 10 hours that you waited or controlling for things like that. So it stands to reason that disruptions, and I think those still need to be characterized, would impact that and impinge on your ability to consolidate or to solidify memories.